maybe. You should take some notes, maybe. You don't have to. It's really close to what we did yesterday. So here we go. The central limit theorem. We talked about a little bit yesterday, proportions. All right. We're going to focus more in on that today. So yesterday, we talked about only problems that involve proportions. So in every single question, they said, blank % of this did this, right? Like 10% of M&Ms are supposed to be green. Or, I don't remember the exact question, but like 8% of apples are damaged or something, okay? That's what the question said. They gave you percentages. So not every single set of data uses a percentage. We talked about lots of things in the very first unit. If we had categorical variables, we probably found a percentage. If we had quantitative variables, though, we didn't find a percentage, we probably found a mean. So if I was asking about everyone's GPA, then I'd probably look for the mean GPA. I'm not going to look for a percentage of GPAs that are a certain number. I'm probably looking for average GPA. So because of that, we have similar ideas to yesterday, but these are specific to when you have a mean instead of a proportion. Okay? So with that being said, the sampling distribution of any mean becomes more nearly normal as the sample size grows. We saw that a little bit yesterday with proportions, right? As the sample size got larger, generally your model got closer to a normal model. Same thing for means. If we check our conditions, which we'll get into in a second, then we should be good. And so it says here, the mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. The larger the sample, the better the approximation will be. So in this case, you don't necessarily have to have a unimodal and symmetric distribution to start with. You could have a skewed distribution as long as you are using a really large sample. It'll counteract that, right? So for means, we just want our samples to be large enough, and then normal model will be perfect. Great approximation, right? So yesterday when we did this, you have to check your conditions. Then you had to identify what the mean and the standard deviation were going to be for your model. Same thing today. We still have assumptions and conditions. They're almost identical. There's only one that's different. We still have the independence assumption, the sample size assumption. And so we have the randomization condition and the 10% condition that back up independence. Those have not changed. However, for sample size, for proportions, we do NP is greater than or equal to 10, and NQ is greater than or equal to 10. Well, for means, we don't have a P, so we can't do N times P. If we don't have a P, we can't do N times Q, because we don't have a Q. All right? So for sample size, you'll need to think about your sample size in the context of what you know about the population, and then tell whether you believe the large enough sample condition has been met. Do you think the sample size is large enough? Okay? Now, that means you have to think about the distribution to begin with. If the distribution in your mind is skewed, then you want to make sure your samples were fairly large to counteract that. If you think the distribution to begin with was unimodal and symmetric, then your sample sizes can be really small and still be fine. So you have to kind of think out the context of the question first. Think about if it's going to be more unimodal and symmetric or more skewed to one side to decide, okay, this sample size they gave me is sufficient or not. Okay, so it's a little bit harder. There's no like cut and dry line like there was with proportions. All right, so that's the only thing that's different. All other assumptions and conditions are the same. So we check the assumption and conditions and everything is fine. Then we need to be able to draw the model. So we already said we're going to approximate with a normal model. And so the mean of the normal model is just going to be the mean they gave you. But we can't use the standard deviation equation we had from yesterday because we don't have a P and a Q, right? So we will be using sigma divided by the square root of n. Right? Sigma is, and I'll go through all this notation again in a second, but the sigma is the standard deviation for the population that they're going to give you. And n is your sample size. You don't have to memorize that. It's on the AP formula sheet just above the one we did yesterday. So it's there for you. But let me go through some notation real fast. Yesterday we talked about how there's a P and a P hat, right? There's a population proportion, and then there is a sample proportion. Same thing here. We have mu, which is the population mean. So they're going to say, here's a population of whatever, and this is the mean of that population. But that means you also have a sample mean. If I'm taking a sample of 50, then I expect my sample mean to
report back to Mr. Crodge's room.
To be close to the population mean, right? But so our sample mean is for our specific sample, and the population mean mu is for the entire population. Just like yesterday, we had P and P hat. With that being said, and these problems are going to be given a sigma, which is a standard deviation of the entire population. But if we were talking about our sample, we would be talking about the standard deviation of our sample. That would be S. Okay, these are going to come into play in later chapters, but you have to keep track of what they're telling you. Are they telling you something about the population or something about your sample? Because later on, that's going to be a big, clear difference in formulas you use. Okay? So just make sure you're kind of trying to keep track of that now. All right, so the sampling distribution model for a mean, very similar proportions. Again, you check your conditions. The only condition that's different is the sample size condition. Is it large enough? The mean of your normal model is going to be whatever you know the population mean to be. And then your standard deviation of your sample will be the standard deviation of the population divided by the square root of n. Okay, so then you can answer questions just like you did yesterday on the homework. I can find probabilities. I can draw models. I can do all the same things. Any questions about that? So I'm going to do two examples. Sort of. I'll kind of breeze through some parts of them. It says researchers measured the waist sizes of 250 men in a study on body fat. The true mean and standard deviation of the waist sizes for the 250 men are 36.33 inches and 4.019 inches respectively. So they're telling you that the population is 250 men. That's the population. They're telling you the mean and standard deviation for that population, because it says the true mean and standard deviations. That's for the 250, the population. In exercise 29, you looked at the histograms of simulations that drew samples of sizes 2, 5, 10, and 20. And the summary statistics for these simulations were as follows. So it gives you different sample sizes and then gives you means and standard deviations based on those sample sizes. All right, based on a simulation. A here says, according to the central limit theorem, what should the theoretical mean and standard deviation be for each of these sample sizes? Remember, so our sampling distribution model is totally theoretical. Okay, so if we were to identify the mean and standard deviation for our sampling distribution model, no matter what the sample size is, what would we assume the center would be at? Where would we assume the center is going to be? I mean, they gave us 36.33. If we wanted to find the standard deviation for our model, then we would take the standard deviation of the population and divide by the square root of the sample size. That's what our models would be based on, right? Our mean that was given to us and the standard deviation based on that formula. So, how close are the theoretical values to what was observed in the simulation? How close are your means that were in the simulation to the actual population mean? Well, they're all about 36.33, right? The larger the sample size gets, the closer it actually gets to 36.33. So they're all really close. What about the standard deviations? If you went through and divided all of these, they're all relatively close too. They get closer to the actual standard deviation from our theoretical model, the larger the sample size gets. That should make sense. It says, looking at the histograms in exercise 29, at what sample size would you be comfortable using the normal model as an approximation for the sampling distribution? So again, it's your determination in this part of the chapter whether the sample size is large enough. Do you think n is large enough or not? So think about what the distribution looks like to begin with. If it's unimodal and symmetric to begin with, then you can use whatever sample size you want. If it's skewed in any way, maybe you need a larger sample size to counteract that. So I'll start at the largest sample size. We have samples of size 20. That is fairly unimodal and symmetric, and so already normal. So I'd be okay with using sample sizes of 20. Seems legit to me. If you're looking at samples of size 10, again, already unimodal and symmetric. The sample sizes of 10 seem to be fine. In sample sizes of 5, we still think that's roughly unimodal and symmetric. So I'd be okay with sample sizes of 5 in this case, because the distribution seemed to be unimodal and symmetric to begin with. The only one I might not be comfortable using is sample sizes of 2, because it seems like it's slightly skewed, a little bit. And so we're using sample sizes of 2 out of 250. That doesn't seem really practical anyway, just to begin with. But if it had been a little more symmetric, maybe I'd be okay using sample sizes of 2. So you need to think about the distribution first. If it's unimodal and symmetric in your mind, then maybe go ahead and use whatever sample size you want. So I'd be comfortable with all of these except for maybe 2, because it seems like it's a little bit skewed. Questions about that? And so D, what about the shape of the distribution of waste size explains your choice of sample size in part C? Again, we want it to be close to normal model if we're going to use that sample size. If it's not, and if it's skewed, we want to use a larger sample size to counteract that. All right, one more example. Assume that the duration of human pregnancies can be described by a normal model with a mean of 266 days and a standard deviation of 16 days. On A, it says, what percentage of pregnancy should last between 270 to 280 days? Has it mentioned anything about a sample size? No. So we're not talking about sampling distribution models in part A. We're just talking about population in general. All right, so it's important to make sure you know what they're talking about in each piece. If I want to find the percentage of pregnancies that should last between 270 and 280 days, what am I going to do? Normal CDF. I'm going to calculate a probability. So I can draw the model if I want to. It's got a center at 266 and a standard deviation of 16. Right? I want between 270 and 280, so somewhere in there. So I could draw out the model in shade, and that would be good for showing that I know what I'm talking about. But I would use normal CDF. What would my lower boundary be? $270, and my upper boundary would be $280, and my mean would be $266, and my standard deviation would be 16. And I could get the probability from that. But it has nothing to do with the sampling distribution model because we're not talking about a specific sample size. Questions? Do I need to calculate that? Or are we good? All right. On part B, at least how many days should the longest 25% of all pregnancies last? So again, we're still not talking about anything with sampling distribution models. We're not talking about a specific sample size. We're just talking about in general. Now, we did this way back in chapter 6, so it's been a while, so I'll refresh your memory. It says at least how many days, some number of days, should the longest 25% of all pregnancies last. So the longest 25% is going to be the top 25%. And our calculator can give us the cut point. It can give us the day that would talk about that. Now we did that in our calculator using inverse norm. It's right under normal CDF in your calculator. Now, for inverse norm, if you're given a percentage and you want the day or you want whatever the cut point is, you work a little bit backwards. An inverse norm only works from left to right. Right? It calculates from 0% up. So if you're interested in the top 25%, then in the calculator you need to talk about the lowest 75%. Is this ringing a bell? All right. So we can't do top 25 because it goes from left to right, so we need to do bottom 75. So we go to inverse norm. It's going to ask for an area. The area is the percentage, so 75. And then it's going to ask you for the mean. It's going to ask you for the standard deviation. So 266 and 16. And it's going to tell you the number of days that the longest 25% of pregnancies last. All right, so we can do that as well. Questions about that? All right, I know I'm not calculating them. I feel like we're okay. On C, suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. So now we have a sample size. I'm talking about a sample of size 60. Let Y bar represent the mean length of their pregnancies. According to the central limit theorem, what's the distribution of the sample mean Y bar? Specify the model, mean, and standard deviation. Right? So what model are we going to use? Normal. And what is the mean going to be? 266. But now that we're talking about a sample of size 60, our standard deviation is not 16 anymore. It's 16 divided by the square root of 60. Because now we're talking about a standard deviation for my sample. Does that make sense? So that answers that question, the model, mean, and standard deviation. Ta-da! You could actually calculate that decimal, but that answers the question. On D, what's the probability that the mean duration of these patients' pregnancies will be less than 260 days? That means we're going to have to use the normal model, so we need to check the conditions. I'm just going to do them verbally right now. We assume independence. Okay? Is randomization employed? No. Do you think 60 women is a good representation of the population? Just 60 pregnant women for a specific doctor. We can go ahead and assume 60 might be a good representation. It doesn't say anything about the obstetrician being a specialist in anything or anything like that. So we can assume it might be a good representation. But this is where things get tricky, right? Is 60 less than 10% of all pregnant women? Yes. Right? Okay. Is the sample size large enough? We have to think about what we thought the sample would look like to begin with, or the distribution would look like to begin with, to decide that. And we're going to get into all of that in the next question. But I just want you thinking about that. Like if you're going to calculate a probability, you need to check your conditions. All right, so on D, what's the probability that the mean duration of these patients' pregnancies will be less than 260 days? How do I calculate that probability? What do I do? Normal CDF. What's your lower boundary and what's your upper boundary? Negative infinity to 260. And then we would use our mean of 266 and our standard deviation of 16 divided by the square root of 60. Right? Just like your homework last night, just we have a different formula for the standard deviation. All right, 39, still the same question. The duration of human pregnancies may not actually follow the normal model described in exercise 37. Explain why it may be somewhat skewed to the left. Why would it be skewed to the left instead of unimodal and symmetric? Premature babies, right? We can have a center, sure. We have a center, but we're more likely to have premature births than we are to have late term births, right? Doctors aren't going to let you be pregnant forever. It's just not going to happen, right? Eventually, there's a point to which they are going to make you give birth to your baby. So it would be skewed to the left, wouldn't it? So if it's skewed to the left, then we can go back and think about some of the things we did in the previous question. Does that change the answers to part A and B? A and B weren't based on a sampling distribution model at all, right? They were just based on a normal model, straight normal model. If it's skewed to the left, is it a straight normal model? No. So we couldn't do A and B if it wasn't normal. Because A and B had nothing to do with sample size or anything. We just assumed we'd unimodal and symmetric information. If we don't, we can't calculate A and B. For C, is it okay if the model is a little bit skewed to the left if you have a sample size of 60? Probably, right? That's what the central limit theorem says. It says if you determine the sample size is large enough, then it can counteract some skewness. And we still use the normal model to approximate the sampling distribution model. Does it make sense why we couldn't do A and B, but we could still do C from before? All right. Any questions on this? It's very similar to what we did yesterday.